today's lesson, we'll take a look at more arithmetic and geometric sequences, as well as neither sequences. Let's start off with our first example here. It says to find the nth term, state if the sequence is arithmetic, geometric, or neither. So keep in mind the idea here is we want to try to go from term to term and see what's going on. I'm going to first start off and see if I have an arithmetic sequence. To do so, we saw how we need a common difference. So if I basically say 3x minus y minus 2x minus 2y, I just want to see what that difference is. So negative y plus 2y, that'll give me y, and 3x minus 2x will give me x. So I would get x plus y. I'm going to do that same comparison, but this time I'll be doing it for the next two terms, which is 4x. I want to see what that difference is between that and 3x minus y. If I subtract that, I will get a positive y, and I'll also get a positive x. Oh, look at that. It looks like we are getting x plus y two times around. Let's see if it actually happens the third time around. So if I do 5x plus y, and I subtract 4x, then again we'll get plus y there. And yeah, it looks like we're getting the same thing, right? So we see here that the x plus y is our common difference. Therefore, I know that this is going to be an arithmetic sequence. In terms of its arithmetic sequence, we know that we are dealing with some kind of equation very similar to a line like we talked about before. So we want some kind of mx plus b format, where the m represents the common difference. In this case, we see the common difference is x plus y. Multiplied by that term number, that x becomes the term number, which we call n. And then we also add the case number 0. So let's go ahead and actually backtrack. If I were to backtrack, right, I want to go back from 2x minus 2y. So if I say 2x minus 2y, and I want to backtrack the x plus y, just like that, then we'll see that we get negative 2y minus y. That'll give us negative 3y, and 2x minus x will give us x. So it looks like my case number 0 would therefore be x minus 3y. And that will be how we find that particular formula, just like this. And we can leave it like that. Okay. On to number 2. Let's take a look at what we're dealing with here. Now these are just concrete numbers, so like we did in class, I'm just going to go ahead and develop my table, because I always like to show my work in a consistent way. I have my term number as well as the value itself, so I'm going to go ahead and write this down. It looks like I have values of 2, and then I have 1, 8/9, 1, and lastly 32 over 25. And oh, sorry, I'm putting that in the wrong spot. Let me do that again. I have a total of 1, 2, 3, 4, 5 terms. So I'm going to write this as 1, 2, 3, 4, 5. And then my term values themselves are 2, 1, 8/9, 1, and 32 over 25, like that. All right, so again, I want to see, is this arithmetic? Well, if it were arithmetic, it looks like I'm subtracting 1 every time, but that doesn't happen all the way through. We're not subtracting 1 every single time. So that's not going to be arithmetic. We can go ahead and cross that out. If it were geometric, then I'd be multiplying by the same amount every time. If I'm multiplying by half, nope, it doesn't look like that's also consistent. So this is not geometric either. This is going to be a neither sequence. I'm going to go ahead and label this as a neither sequence. Okay. So if it's a neither sequence, we just need to figure out what that property is based on not looking at a common difference or common ratio. And the idea here is you want to find a formula that somehow links the term number. So look at all these numbers here, right? The 1, the 2, the 3, the 4, and the 5. We want to somehow see how that is related to anything on this side here. As we take a look at these values, you'll notice actually a few of them have some fractional values in here. And you want to try to find a connection between the term number and whatever you're seeing as the value itself. To me, what I notice here is that term number, the 3, that actually kind of plays a role. How do I think about 8? I mean, I could think of it as like a 2 to the 3rd power, right? That's technically 8. And then the 9 is also the same thing as 3 times 3. I could think about it like that. And then as I look at the 5, the 32 over 25, what I notice is, again, how do I get 25? I can see that's going to be 5 times 5. And then on the top, I have 32, and so I want to somehow link 32 with 5. Well, that's just going to be, what, 2 times 2 times 2 times 2 times 2, right? We see that that's also an exponent, repeated multiplication there. I'm going to go ahead and write that as 2 to the 5th power. So I do see that that's happening, and I actually see that there's a correlation between those two terms there. It looks like I kind of have a pattern in play. Now you'll notice that the second term and the fourth term also both have a value of 1, but I could also rewrite that 1 in a different way, right? I could say it's technically a fraction too. Now, as I look at the pattern, I saw I went from 3 times 3, I skipped something, and then I went 5 times 5. I wonder if what I skipped was a 4 times 4. And therefore on the top also, I went from 2 to the 3rd power, I went over to 2 to the 5th power as I skipped something in between. I wonder if that's 2 to the 4th. I know 2 to the 4th is 16, and 4 times 4 is also 16, and oh yeah, that actually gives me 1, right? So it looks like I'm developing a rule here. I just want to verify if this works every time. So I notice that on the top I have 2 to the power of something. If I went down 5, 4, 3, this must be a 2, this must be a 1. On the bottom I went 5 times 5, 4 times 4, 3 times 3. I wonder if this will be 2 times 2, and maybe this is 1 times 1. Let's double check our work. Let's see if that's accurate. 2 to the first is 2 over 1. That gives me 2. Yep. Over here we get 4 over 4. That gives me 1. Yeah, this works. All right, so I think we found our rule. Here it is. Grand finale. We see that we have 2 to the power of the term number, n. That's what's linked over on the x column of our table. Over, and then the 5 times 5, 4 times 4, 3 times 3. That's again going to be that nth term, and you're squaring it. And there is our rule, just like that. Okay? So that one was a bit trickier. You'll notice that when it comes to neither sequences, as I mentioned in class, it's really helpful to develop this table. So that way you can see how any kind of term numbers, as you go in sequential order, 1, 2, 3, 4, 5, it may help you to see what kind of patterns you see on your right-hand column. Okay? All right, let's go on to number 3. Here it says that what if the sequence 5, 20, 4x minus 1, what if it was arithmetic? If it was arithmetic, we know that as we go through from term to term, we should see a common difference. So, 5 plus something should give us 20. 20 plus some same number should give us 4x minus 1. So if it's a common difference, well, we definitely know 5 to 20, right? That's pretty concrete. It looks like we're always adding 15, right? So add 15, we add 15. Well, what that means is that the third term should be 20 plus 15. That'll give us 35, and that should equal 4x minus 1. So from here you can solve for x. You're going to get 36 equals 4x, and therefore x is 9. And we're just being asked to find what x is. There it is. Okay? Now, what if the sequence were geometric? Well, again, if we have 5, 20, 4x minus 1, you think about, again, how you go from term to term. But this time, if I'm getting a geometric sequence, I should be multiplying. 5 times something gives me 20. Well, that'd be 4. So if it's geometric, it should always be the same ratio, which means 20 times 4 should give me 80. And I know 80 is equivalent to the value at 4x minus 1. And from here, I can then solve. 81 is equal to 4x, or 81 fourths is the value of x, just like that. Okay, so you can see here that what we can do is just by establishing the sequence, just kind of setting it up. Like for example, number 4, they tell you t sub 2, that's the value of 2. If you just set it up, and it really helps to see it in action, you have t sub 5 as well. So here's t sub 3, here's t sub 4, and here's t sub 5. It really is nice when you kind of set it up so you can see what's going on here. What we want to find is t sub n, or sorry, t sub 10. So I'm going to put t sub 10 over here. We do know that t sub 5 is 16, just like that. And just like we did on problem number 3, you can basically just say, well, how do I get from 2 to 16? I'm starting at 2, and as an arithmetic sequence goes, I am adding 1, 2, 3 times. I'm adding a common difference 3 times, and I get the value of 16. right? From there, we can solve for the common difference. We're going to get 3d is equal to 14. So, we're getting a common difference that is 14/3, right? Knowing that, we can see that from t sub 5 to t sub 10, you actually know that you're going to have to add another common difference. It looks like 5 times, right, to go from 5 to 10. So you can say, okay, I've got a common difference of 14/3. I'm going to have to add this 5 times, and then I'm adding it to what? I start off with this value at 16, so I can add 16 there, like that. Okay, let's see what we get. 14 times 5, that's going to give us 70/3 plus 16. Let's go ahead and change that to common denominators. That's the same thing as 48/3, and so we'll get 118/3, like that. Okay. All right, letter B. Similar approach. Again, you can kind of say, okay, well, I've got t sub 2 here. That's the value of 2 still. T sub 3, 4, and 5. T sub 3, 4, and 5. And at t sub 5, I'll be at the value of 16. We want to get to t sub 10, just like that. Okay, so again, similar approach. Same idea. Say, okay, I'm starting off at 2. I'm going to multiply 1, 2, 3 times, right? So we say 2, we're going to have 2, and we're multiplying by a common ratio 3 times. And that should give us the value of 16. R cubed is therefore going to equal 8. So R cubed equals 8. That means that R is 2. So our common ratio is 2. So what we're saying then is, again, if we want to just look for t sub 10, then I'm saying, okay, let's imagine we start at 16, and how many more ratios do we need to multiply to get to t sub 10? I'm going to need 5 of them. So 16 times r to the 5th is going to give me the value I want, right? And what's the r value? Oh, it happens to be 2. So we have 2 to the 5th equals, and then we can go ahead and multiply that together. So we get 2 to the 5th, that'll give us 32, and 32 times 16, let me just get my calculator out, is going to give us 512. Okay, and there we go. T sub 10 is 512. And so it's important to note what I'm writing here now, t sub 10. So the notation I'm writing here, you'll notice we've written this a lot of subscripts. If you see t sub 1, t sub 2, t sub 3, whatever it is, this is basically telling you your, this is like the first term, this is like the third term. So just knowing how to interpret these things, okay? And this is like your nth term. I did see in class that some people were maybe using different variables. Some people like to use a instead, so this also works, you can say this, okay? Yeah, so any of those forms would work, okay? All right, let's go on to the next page. So here we're going to take a look at another sequence, 1, 3, 6, 10, 15, same idea. We just want to find what that pattern is. So just like we did on the previous page, if I need to, I'm just going to go ahead and set up my work in the form of a table. And I have 1, 2, 3, 4, 5 terms. 1, 2, 3, 4, 5 terms. And my numbers are 1, 3, 6, 10, and 15. So from here, what I'm going to do is I'm going to try to get my arithmetic or geometric sequence again. So let's see, I'm going to add 2. I'm going to add 3. Oh, nope, that's not arithmetic. I can see that's not arithmetic, right? Let's go ahead and try geometric. So I'm going to multiply by 3. Nope, it doesn't multiply by 3. So this is also not geometric. This is going to be a neither sequence. Okay, so if it's a neither sequence, let's see what we're actually dealing with. One thing I'm going to try, I'm going to go back to the arithmetic mode, and I'm going to add, and I'm going to see what's happening. As I add, I notice actually, as we go through this, take a look at these numbers here. You'll notice that the numbers, as we do it a second time around, now we actually get a common difference. There it is, plus 1, plus 1, plus 1. It happens a second time around, right? And one thing that we talked about in class, when this happens, when you get a common difference the second time around, let's call it the second iteration, then what this is leading you on to is understanding that there's some kind of quadratic pattern here. It's some kind of like x times x, right? Or n times n, something like that. And so I don't exactly know what kind of quadratic this is going to be. Maybe it's like, n squared plus 3n plus 4 for all I know. I really don't know. And so it could have that tail end where it's not simply just the n squared. When we were looking back at our notes, we saw an example where we did simply just get n squared, right? And that one was, where was that one? I think it was over here, right? When we saw this rule right here. 1, 4, 9, 16. We ended up just saying, yeah, that was a pretty simple quadratic. But in this case, let's see what we actually have, okay? So I'm going to go ahead and now get our numbers here. 1, how do we get that? Well, as a quadratic, I told you, it's kind of something times something. So I'm just going to go ahead and create some blanks. That 1 is something times something. That 3 is going to be something times something. 6, I'm just going to go ahead and just give it a little framework to say each of these numbers are multiplying two things together, just like this, okay? And at this point, it's going to actually be a little bit of an educated guessing and checking. And so what you can do here is just fill in some numbers. The best thing you can do is just write numbers in. The worst thing to do, you don't do anything at all. Because when you don't do anything at all, you're not really able to see what works and what doesn't work, and you're not really checking anything. So you just start off right off the bat just saying, well, what's the easiest thing you can think of? Like, for example, what's the easiest thing you can think of? What times what gives you 1? My first instinct is literally just 1 times 1, right? What's the easiest thing you can think of when you think of 3? Literally, the first thing that comes to my mind is 3 times 1, yet again, okay? So I know that, maybe these numbers may or may not work, but the trial and error is going to be the key piece to this, just to see what's going on, okay? So I'm going to try it again. Let's do 6. Now, 6, I'm not going to keep saying something times 1. It doesn't make sense to go 6 times 1, 10 times 1, 15 times 1. You did yourself no good service in doing this. I would not recommend doing this, okay? So instead, just try to find other numbers that work. So for example, when I think of how can I get 6, well, maybe now I'll actually say 3 times 2, something else. What do I think of when I think of 10? The easiest thing I can think of, I think of 5 times 2. What's the easiest thing to think of when I think of 15? I think of 5 times 3, right? So here we have written some numbers out, and this is going to be kind of like a little bit of, again, an educated guess in terms of what these values are, but also at the same time, you trying to also find patterns in the numbers you've created. Do I see patterns? Well, I'd love to talk about this with you in the class, but if you are not in class, let's take a look at the patterns and maybe expedite this process just a little bit. Maybe one pattern you see is that this is 1, 1, this is 2, 2, and so you can maybe expect, oh, I'll have a 3, 3, right? Maybe I see 1, 3, 3, 5, 5. That could be a pattern you see there. It works, but at the same time, the numbers also need to be changing as I go from term to term. So it does work. There is that pattern, but it may not be the most beneficial pattern. So I'm going to try something else instead, okay? And again, this is just the idea of guessing and checking and me thinking out loud here. But another pattern I notice is I did go from the number 1 itself, maybe to the number 2, and then from 2 to 3. And the way I did that was I did start at this one, and then I went to 2, and then I went to 3. If I kept in line on the same side, you'll notice I also went from 1, and then I went to 3, and then I went to 5, because I need to make sure that these hold intact. I don't want to disturb any of these numbers, okay? Now, that means that my other middle numbers can be disturbed. These are probably not the numbers I want. I'm going to go ahead and erase them, okay? So I'm going to get these numbers out because maybe those were not working in my favor, okay? Remember what we had was like a 3 times 1, but that wasn't really in my favor. If I want to go from 1 to 2, I did skip something. I wonder if what I skip is instead, maybe I'm going in order. Maybe I'm going from 1 to, oh, look at this, 1 to 3. I wonder if I'm just skipping some number. What if I want to go 1, 2, 3, 4, 5. I'm going 1, 2, 3, 4, 5. There we go. So I have now created a pattern where I go in sequential order. 1, 2, 3, 4, 5, just like that. Similarly, on the next, the right-hand column, I went from 1, skip something, 2, skip something, 3. I wonder if what I'm skipping is technically a 1.5, or how do I write that? That's 3 over 2. 1, 1.5, 2. Maybe this is 2.5. 2.5 would be 5 over 2. And then 3. 1, 1.5, 2, 2.5, 3. Let's give it a try. Let's see what happens. Okay? I know it's getting really messy with all these colors, but 1 times 1 is 1. 2 times 3 over 2, well, the 2's cancel out and we get 3. 3 times 2 gives us 6. 4 times 5 over 2, the 4 and 2 cancel out, we get 2. 2 times 5 would give us 10. And 5 times 3 gives us 15. There we go. So we have actually established a rule. What do we have? The left-hand column is literally 1, 2, 3, 4, 5. It's coming from the nth term. It literally is n. So in my expression, this is literally just n. How do I go from 1 to 1.5 to 2 to 2.5 to 3? What am I doing every time? Actually, if you want, you can, in a way, call this its own little arithmetic sequence, right? To go from 1 to 1.5 to 2, what am I adding every time? I'm adding like half basically, right? Adding half, adding half. I'm adding half every time. So it looks like this particular rule would have a half, right? Actually, if I think about it another way, you can also see how this 3 over 2, the 5 over 2, it has the half in there. I went from 3 over 2. 2 is the same thing as 4 over 2, and then 5 over 2, and then this is 6 over 2. Oh, let me rewrite that. All right, this is getting messy. Here we go. This is 3 over 2. This is 5 over 2, but 2 is the same thing as 4 over 2. 1 can be called 2 over 2, and 3 can be called 6 over 2. Notice how they all have something in common. They all have an over 2. And then we went 2 to 3 to 4 to 5 to 6, just like that. How do you get 2, 3, 4, 5, 6? Well, it's coming from 1, 2, 3, 4, 5. So how do we get from 1 to 2, 2 to 3? We're always taking n and adding 1 to it. And there we have created our rule, just like that. Okay? To find the 100th term, the next part of the question says, well, let's just plug it in. If I want to find n is 100, then 100 times 101, basically, n plus 1, 101, divided by 2. That'll give us, what, 50 times 101? That'll give us 5,050, just like that. Okay? So that is one example on how we can use patterns to help us create the rule. I'm going to leave the rest up to you.